Hello dear friends, welcome to this video. In this video, we'll be discussing the application of second and third isomorphism theorem in ring theory. Whenever we study ring theory, we have seen that the first isomorphism theorem is used very frequently. But the application of second and third isomorphism theorem were never discussed in our syllabus. So today, I'll come up with two simple applications of second isomorphism theorem and third isomorphism theorem. As you see on the screen, I have given second isomorphism theorem as if I and J are the ideals of the ring R and my I is also an ideal of J. Okay, first question might arise, you might be calling this as a third isomorphism theorem. But the number doesn't matter, right? As its name doesn't matter in mathematics, giving a number to a theorem doesn't matter. So you can consider this as your second isomorphism theorem. The first isomorphism theorem is fixed. That's about a ring upon kernel is isomorphic to the image. That is always fixed. But the second and third has no order. Right? So let's see what this theorem is. I and J are the ideals of ring R. I is again an ideal of J. Then by the theorem, my R quotient J, the whole quotient with J quotient I would be isomorphic to R quotient J, right? So that is something that theorem tells us. Let us just have an application of this. So first thing is I should have two ideals of the ring R. Let's talk about this two ideals of the ring R. The most simple ring that recollect is nothing but Z. So in Z, I consider two ideals. In Z, suppose I consider my two ideals as 2Z and 3Z. Now the first question arises, can I say my 2Z and 3Zs are the ideals of R? Yes, they are principal ideal, but either of them is not an ideal of each other. Can you see that? Right? I cannot say that 2Z is an ideal of 3Z or the 3Z is an ideal of 2Z. So what I do, I just try to get an application. So I just write this as a 4Z. Now it is looking wonderful, right? What I can see is my 2Z and 4Z are ideals of Z. Also, my this 2Z is nothing but a bigger set than 4Z, right? So my 2Z contains 4Z. Therefore, my 2Z will contain this as an ideal. So I can write like, therefore, my 4Z is an ideal of 2Z. Right? So, by second isomorphism theorem, as you see, I am giving this theorem as a second isomorphism theorem. So, by this theorem, I can write my Z modulo. What is on the place of I? On the place of I, what I observe? Who is there on the place of I? I is nothing but this 4Z. Right? So, over here I am considering this as 4Z. This is 2Z. This is Z. Right? Hence, my 4Z is an ideal of 2Z. Right? Everything is working well. So, it is Z modulo this 4Z congruent with 2Z modulo 4Z is isomorphic to that 4Z will vanish and I get Z modulo 2Z. More precisely, that is nothing but Z2. Right? So if you see very carefully what we have proved that if we have a two quotient and you again make a quotient, you get a new ring of the quotients, and the rule to get a new quotient is given by the this second isomorphism theorem. Right? So this is a small application of this theorem. Right? Let us just see a similar kind of an application of the third isomorphism theorem as well. If I call that as a second one, I will call this as a third one. If R is a ring, I is an ideal of R, S is any subring of R, then my I plus S modulo 2I Now, first thing is you should know how I plus S is defined, right? There are multiple things in this theorem that need to be proved. The first thing students should prove that I plus S is a subring of R. Also, I, whatever I you got, should be the ideal of I plus S. That is another thing to prove. And after all this, what the theorem tells you is I plus S modulo I is congruent to S modulo I intersection S. So this is few more things that you have to prove. You need to prove that I intersection S is again an ideal of S, right? If you prove all this thing, at the end we get to this final statement that if you have I plus S modulo I or the quotient I, then it is isomorphic to S intersection with I as a module of S, right? So this is something that is given by the third isomorphism. As I said, we are looking for the application. To get an application, again we'll be working in Z, because Z are nothing but the origin of rings, right? Whatever definition that we have arise in the ring is just the properties of Z which we want to generalize. So let's see an application based on Z only. But before that, I would like to share a few important results. What is it result? If you see, if you have NZ and MZ, these are nothing but two principal ideals of Z. If you are trying to add them, the answer of this two would be same as the GCD of Mn times Z. For an example, suppose if I have my 2Z plus 6Z, right? The answer is going to be 2Z only. Suppose it is 12Z plus 6Z, answer is going to be 6Z, because what I'm writing on the right hand side is nothing but the GCD of two numbers, right? For an example, I take 9 over here, right? So what I should write over here? 12, 9, GCD is nothing but 3. So answer is going to be 3, right? So this is something that you are supposed to understand. Similarly, if you have this MZ into MZ, then the answer is going to be LCM of NM times Z. For an example, let me just take 12Z into 9Z only. I'm taking a product. There is a way to define products of ideal as well. You should search how to define the product, how to define the addition of two ideals also, right? So if I'm just multiplying this, what I know, I just should take the representative as nothing but the LCM. So what is an LCM of 12 and 9? I can see it is going to be 36. Is it fine? So this is nothing but the important result, and I have tried to explain with an help of an example. But we are interested in the application of this theorem, which I am calling today as a second or the third isomorphism theorem, right? So again, I will try to take this similar example over here. What is that example that I would try to choose? Again, in my Z, we know that any NZ and MZ are actually nothing but the ideals. More precisely, they are the principal ideals. But I write it as ideals of Z, right? So if they are the ideals of Z, by this third isomorphism theorem, what I can write is I can write my NZ plus MZ mod any number I'm trying to write. I'm trying to write it as NZ, right? And that is isomorphic to what I'm dividing with. I'm dividing with NZ, right? So if I'm dividing with NZ, then it becomes MZ modulo NZ intersection with MZ. So I would like to correct myself. Sorry, my dear students. I would like to correct it. While writing the dot over here, it is actually nothing but the intersection. While writing this theorem, I recall that this operation was the intersection, right? Because what we have learned is when you add it, you get a GCD. When you take intersection of them, that is a common part of them, it would be generated by the LCM of two numbers, right? So I'll just correct myself over here as well, right? So we should learn from the mistake, and I think I and you all will remember now. Whenever we take an intersection, it should be LCM. Whenever we take an addition, it should be GCD, right? So ultimately, what we found is if I take NZ plus MZ upon NZ, that is isomorphic to, mz upon nz intersection with mz. Right? That is nothing but the last statement that we have got. Let's come over here. Can we just generalize this further? As we have learned, whenever you add, you get the GCD, right? Whenever we add, we get the GCD. So my numerator is GCD of nm z modulo with nz. The answer is isomorphic to taking mz modulo with LCM of nm z. Right? Can you see, this is so much interesting. This is how we obtain just by using the third isomorphism theorem of Ring. Now, how you can see, this is a interesting part. If you just see the representative set, right? What are the representative of the set? It is GCD of nm in the numerator. Over here it is n. Over here it is m. And over here it is LCM of nm. So what I'm writing is, I'm just writing the representative of those ideals in the order in which, in the pattern in which they were appeared. What I say is, if just I cross multiplying, just by cross multiplying, we can get a wonderful result which we have in the integers, that is GCD of two number into LCM of two numbers is equal to n into m. So this is so wonderful that just by using this, I'm not saying this we can write like this, we cannot write like this, but what I'm trying to tell you, we are just making an observation of what we have got and what pattern it is trying to tell us, right? So that's about the application part of it. Again, I'll just recall that whenever you have intersection, take LCM. Whenever you have addition, take GCD. That is one of the important results when you're studying in TYBSc, right? So that's all about this video in which we have seen the application. If you like this video, please subscribe and share it with your friends. Okay, bye bye.